Hello once again. Today we are going to discuss about syllabus from CHA 391, section 2nd, analytical extraction techniques. So you have learned about pre and post extraction consideration in the first chapter, and in that we had discussed about the solid extraction sample strategies, solid, aqueous and air samples, how we can sample them, and chromatographic methods of analysis and sample concentration methods. So in that part, how the sampling process is involved or done for chromatographic separation, if we are going for pre-sampling or post-sampling, and then what are different extraction techniques that are employed for solid, liquid or gaseous sample that we had discussed in the first chapter. Now we come to the next part of classical approach for aqueous extraction. So samples in aqueous phase, how they are extracted and how they are prepared, that we are going to learn in this second chapter. So the objective of liquid-liquid extraction is to be aware of approaches for performing liquid-liquid extraction of organic compounds from aqueous sample, to understand the theoretical basis for liquid-liquid extraction, and to be able to select the most appropriate solvent for liquid-liquid extraction. The next is to understand the practical aspect of liquid-liquid extraction. So we are going to learn about this we are going to have more focus about the theoretical background, and we have already learned in the lower classes about solvent extraction. So this all gives us the idea about the principle, underlying the principle. So we are going to learn about the practical aspect of liquid-liquid extraction further in this chapter, and to appreciate the practical difficulties that can arise in performing liquid-liquid extraction and their remedies. What are the solutions to overcome these difficulties that we are going to see. And the last point is to be aware of principle of operation of purge and trap and its application that we are going to see when the emulsions are formed. So let us begin with the liquid-liquid extraction. So liquid-liquid extraction has the principle that a sample is distributed or partitioned between two immiscible liquids or phases in which the compound and matrix have different solubilities. Normally, one phase is aqueous, often the denser or heavier phase, and the other phase is an organic solvent, that is the lighter phase. The basis of extraction process is that the more polar hydrophilic compounds prefer the aqueous, and the more non-polar hydrophobic compounds prefer the organic solvent. So that is the basis how we are going to involve the separation of the sample components in these two phases. So the theory of liquid-liquid extraction, let us talk about how we are going to apply it theoretically and derive some terms so that we can equate the concentration that are obtained, or after extraction, how much is the amount left unextracted, or what is the efficiency that we can relate with this theory. So the two terms are used to describe the distribution of compounds between two immiscible solvents, namely the distribution coefficient and the distribution ratio. So this distribution coefficient is similar to that what we have discussed about in chromatography, partition coefficient. So the distribution coefficient is an equilibrium constant that describes the distribution of compound X between two immiscible solvents. For example, an aqueous phase and an organic phase. For example, an equilibrium can be obtained by shaking the aqueous phase containing the compound X with an organic phase such as hexane. This process can be written as an equation: X in aqueous phase going in forward and backward direction arrow with an X in the organic phase, where AQ and ORG are the aqueous and organic phases that are represented in this equation. So the ratio of the activities of X in the two solvent is constant and can be represented by Kd is equal to X ORG, that is X in the organic phase, to the concentration of X in the aqueous phase. So where Kd is distribution coefficient. While the numerical value of Kd provides a useful constant value at particular temperature, the activity coefficients are what we are going to have undefined. So a problem often encountered in practice is to determine what is the most efficient method for removing a substance quantitatively from solution. So it can be shown that if V ml of say an aqueous solution containing x0 grams of solid be extracted in n times with small V ml portion of a given solvent, then the weight of solute xn remaining in the water layer is given by the expression. So we have derived this equation also in the lower classes. So we are not coming into the derivation part of the equation, but here we are relating an what we can consider the term xn that tells us the weight of the solute remaining in the water layer, from which we are want to extract the solute component. So that can be given by x0 in bracket capital D, that is the what we are considering distribution ratio, into capital V, that is the volume we are using, what we are considering of the aqueous phase, and small v we are taking the volume or portion of solvent used for extraction. So for example, we are extracting with 5 ml of organic solvent 2 times, then small v will be 5 ml and n will be 2. So this is the way we can find out with this equation how much is the amount of solute left or remain after extraction n times of the component that we want to extract. So where D is the distribution ratio between water and the given solvent, it follows therefore that the best method for extraction with a given volume of extracting liquid is to employ the liquid in several portions rather than to utilize the whole quantity in a single extraction. So this may be illustrated by a following example. We'll take an example and we will see how we can go with this equation. Suppose that 50 ml of water containing 0.1 gram of iodine are shaken with 25 ml of carbon tetrachloride. So that is an example taken. We want to extract 0.1 gram of iodine from water into carbon tetrachloride. So we are using capital V is the volume of aqueous layer that we are taking 50 ml, and what we are having initial weight of the iodine in water, that is 0.1 gram. And how much is the volume that is taken for organic layer? It is 25 ml. So small v corresponds to 25 ml. So now we know from the literature value the distribution coefficient of iodine between water and carbon tetrachloride at the ordinary laboratory temperature is 1 upon 85. So this gives us how much will be the amount distribution of solute iodine into aqueous, what we are going to have from aqueous to into organic phase. So that is at equilibrium, the iodine concentration in aqueous layer is 1 by 85th of that in carbon tetrachloride. So once you check that organic layer carbon tetrachloride, you are going to achieve an equilibrium of iodine concentration in aqueous layer to the carbon tetrachloride. It will have an 1/85th of that will be in carbon tetrachloride. The weight of iodine remaining in aqueous layer after one extraction with 25 ml and also after 3 extraction with 8.33 ml of solvent can be calculated by application of the above formula. So we are going to have the weight of iodine remaining in the aqueous layer, what we can find out after with an extraction of 25 ml and also after 3 extraction with 8.33 ml of the solvent, that can be written in a formula, and it can be written as x1 gram of iodine remains in 50 ml of water and its concentration is x1 upon 50. It is the concentration that we are expressing as how much is the amount grams per milliliter. So initial weight that we were having now will be reduced to x1 gram. That will be the amount after extraction left over. That can be given as x1 upon 50. It will be having an unit as grams per milliliter. So the concentration in carbon tetrachloride layer will be 0.1 minus x1. We are extracting 0.1 gram, from which we are having now left over is x1. So obviously, how much will be the concentration of iodine in carbon tetrachloride, it will be 0.1 minus x1 upon 25 ml. So 25, that will be the amount that we have taken for aliquot used for extracting uh, iodine from aqueous layer. So that can be given as 0.1 minus x1 upon 25 grams per milliliter. So we can write here that x1 upon 50 by using the equation that we have already written, x1 upon 50 upon 0.1 minus x1 upon 25. That will be distribution coefficient, that is concentration in what we are going to have aqueous layer to what we are going to have the concentration in the organic layer. That will be equal to 1 by 85, or we can write it as equal to x1 is equal to 0.00230 gram. So the concentration in aqueous layer after 3 extraction with 8.33 ml of carbon tetrachloride is given by x3 is equal to, so by substituting in the initial equation that we are writing as how much is the quantity left over, we can have 0.1, what was the initial weight of the iodine that was taken, into what we are going to have in the numerator, D is 1 upon 85, capital V is the 50. So what we are going to have the next in the denominator, so that is 50 upon 85 plus what is the small aliquot that is taken for extraction is 8.33, and that we are going to have the N, small n, that will represent 3. So how much is the quantity after calculating it in this equation? By performing the stepwise calculation, we get the value of x3 left. What we are going to have 0.0000287 gram. So this extraction may therefore be regarded as virtually completed. From 0.1, we are going to go towards what we are going to have 10 raised to minus 4. That much what we are going to have the leftover concentration. That means virtually we have extracted all the iodine from the aqueous layer. All right. So I hope you understood how we applied the equation for finding out amount left over in the solution. Now we come to the next term. If we confine our attention to the distribution of solute A between water and organic solvent, we may write the percentage extraction E% as E% is equal to 100 into A0 upon V0, where we are going to have VO indicating or 0 indicating organic layer and W indicating aqueous layer. Then we can write it as 100D upon D plus VW upon V0. So simplifying this equation to find out what we are going to have the percentage extraction, that can give us the idea about how efficiently we are performing the extraction. So this equation actually helps us to know at what amount from 100% we have extracted it into. So where V0 and VW represents the volume of organic and aqueous phases respectively, thus the percentage extraction varies with the volume ratio of two phases and the distribution coefficient. So as you change the volume ratio, it changes the percentage extraction. So it is always recommended that instead of using a larger volume in one single step, we can use or divide that larger volume into small aliquots. Suppose we want to extract 50 ml of aqueous layer with 25 ml of organic layer. We are going to take, instead of taking 25 ml in one single step, we can have the extraction carried out by 5 times 5 ml volume of organic layer. That gives us better efficiency. So if the solution contains two solutes, now up till now we were discussing about if the solute component is only single one, like iodine that we discussed in the previous example. But now if the sample sample contains two components, A and B, it often happens that under conditions favoring the complete extraction of A, some B is extracted as well. That means it will also contribute for some distribution into organic layer. So we should have a condition where the solid molecule A should get separated from B, then it should have a larger distribution coefficient difference between A and B, then only effective separation can get achieved. With this terminology, we can apply the effectiveness of separation increases with the magnitude of separation coefficient or factor beta. So we represent that the separation coefficient magnitudes with a factor beta, which is related to the individual distribution ratio as follows. So beta, we can write it as A0 upon B0 upon AW upon BW. So actually what is A0, B0? It indicates what we are going to have distribution in organic layer of A and B. So we are going to have A0 upon AW. We can write it as distribution coefficient of A, and B0 upon BW. We can write it as distribution coefficient of B. So beta gives us the ratio by which the distribution coefficient of A varies with the B. Suppose, for example, if DA, that is distribution coefficient of A, is 10 and distribution coefficient of B is 0.1. So a single extraction will remove 90.9% of A and 9.1% of B. That is the ratio 10:1. We are having this distribution ratio that is indicating beta, that we consider separation coefficient, how that can give separation of A from B. So in one extraction, we were having 90.9% of A extracted into organic layer as compared to 9.1% of B. If we continue extraction with another alicon, so a second extraction of the same aqueous phase will bring the total amount of A extracted up to 99.2%. So if we substitute that value, we can get a 10:1 ratio. If we have to attempt it in the second step, we are going to have increased magnitude of A, but along with that, there will be subsequent increase in the value of concentration of B also. So the value reached from 9.1% of B to 17.4% of B in the second step. So the ratio will now become 5.7:1. So first initially the ratio was 10:1. Now the ratio became 5.7:1. So more complete extraction of A thus involves an increased contamination of B. So in such cases, we need to focus what is the separation coefficient value. If we are having a single component, there will be no what we can consider the choice. We can go for multiple extraction. Multiple extraction will increase the efficiency, but if we are having more than one component, we have to also look into the value of separation coefficient beta, and that should be of larger difference in the distribution coefficient values. Then only we can have a single extraction which will give us an contamination of B that can be avoided. So now we come to the what we can have, how we can carry out the solvent extraction steps and liquid efficiency of extraction, how we can improve. So selectivity and efficiency of liquid-liquid extraction is critically governed by the choice of two immiscible solvents. Often the organic solvent for liquid-liquid extraction is chosen because of its, first thing, low solubility in aqueous phase, that is typically less than 10%, it should have immiscibility. Then only we can have the organic solvent chosen for liquid-liquid extraction. Second point, on basis of what criteria we are selecting solvent, that is high volatility for solvent evaporation in concentration stage. So we have already discussed that in chapter 1, pre and post extraction. So we are going to have this problem when we want to extract. After extraction, we want to enrich the sample. So concentration of the solute molecule that we want to achieve finally in a refined form, then we need to have high volatility of solvent that is chosen for liquid-liquid extraction. The step third, where we are selecting solvent on basis of high purity. So directly linked to the solvent evaporation process described above, so which could pre-concentrate any impurities within the solvent. So solvent, if we are evaporating, obviously if impurities are there, they also get enriched, and enrichment will give us the error in the solute properties or solute composition. The next is compatibility with choice of chromatographic analysis. So it should be compatible with what we are going to have the different chromatographic analysis that we are going to carried out after extraction of that sample. Whatever processes are carried out on that sample, it should be compatible, then only that solvent can be utilized. For example, do not use chlorinated solvents such as dichloromethane if the method of analysis is GC-ECD. So that we have already discussed, ECD, electron capture detector. If we are having the solvent itself, chlorinated solvent, then instead of having the solid molecule getting electronegative charge or electron capturing, solvent itself will capture, and that will interfere in the analysis. So, or strongly UV absorbing solvent if you are using HPLC UV. So if you are going with an HPLC analysis and UV analysis, if solvent itself is absorbing in the UV range, then it will be having the problem in the analysis of solid molecule, which will be of very small concentration as compared to the mobile phase or whatever solvent we are using for extraction. So if that is compatible, then that will be selected with as a solvent system in liquid-liquid extraction. And the last point is polarity and hydrogen bonding properties that can enhance compound recovery in the organic phase. That is, increase the value of Kd that we have already seen in the previous discussion. So two distinct approaches for liquid-liquid extractions are possible. That is discontinuous liquid-liquid extraction. So these are the two ways by which we are going to carry out liquid-liquid extraction. This is classically we have studied in solvent extraction process. Discontinuous indicates we are having aliquot taken and extracted by a separating funnel. So this is the discontinuous liquid-liquid extraction where equilibrium is established between two immiscible phases, or continuous liquid-liquid extraction where equilibrium may not be reached. So we are achieving this two type of liquid-liquid extraction processes. In case of discontinuous, we are using a separating funnel, and discontinuous will be using an what we can consider the continuous boiling and condensation. So we are going to have a condenser reflux assembly in case of discontinuous extraction. Continuous will achieve equilibrium, discontinuous will not achieve an equilibrium. Let us talk about the first one. In discontinuous extraction, the most common approach uses a separating funnel. So we are going to see the reason. We are already aware about the separating funnel. You have already used in the lower classes for extracting sample. We have performed an experiment also, extraction of Fe with that hydroxyquinoline in carbon chloroform and from aqueous layer. So we are having that experiment performed. So you are aware about the separating funnel. So the aqueous sample is introduced into a large quantity into a separating funnel. We will see how the working is. Let us talk about the solvents for liquid-liquid extraction. Aqueous solvents are water. Water immiscible organic solvent will be hexane, isooctane, petroleum ether, or other aliphatic hydrocarbon. Acidic solution, diethyl ether we can use, combination of. Basic solution, dichloromethane, high salt, salting out effect. That can be complexing agent, ion pairing, chelating, and chiral. We can go for ethyl acetate. Any two or more of the above, we can have aliphatic ketones, aliphatic alcohols, toluene, xylenes, that can be having the any two what we are going to use that them in the combination. So separating funnel, we are going to have a Teflon stopcock where that can be used, and 60 ml of suitable organic solvent we are going to mix. For example, dichloromethane is added. A stopper is then placed into the top of the separating funnel, and separating funnel is then shaken manually by placing the stoppered end of the separating funnel into palm of the hand, and inversion of the funnel can take place. So this process is repeated for approximately 1 to 2 minutes, inverting the separating funnel approximately 5 to 6 times. So we are going to have this replacement by placing the stoppered end of the separating funnel into palm. That indicates that you should not have any leakage from the what we are going to have stoppered end of the separating funnel. This process you many times whenever you are performing it practically extraction process with separating funnel, you don't perform it in the same way. You always hold it in the vertical form and you shake it in the circular manner in the upward style only. But actually when you are going to have this process done, we have to take into account that the two layers are homogeneously blended by shaking it in the inverting it into our hand and then placing it again. In between you have to remove the stopcock so as to release the pressure. So wherever you are going to have some release of pressure that has to be met, you are going to remove the stopcock in when it is shaken vigorously to release the pressure, so that we can have the layers that can be separated uniformly. Okay, so that is for discontinuous liquid-liquid extraction. This is for continuous liquid-liquid extraction. So we are having a round bottom flask shown over here. So we are going to have separation of the liquid layer, organic layer, that can be done by and reflux done, and we are going to have condensation. So continuously we are going to have this pure form of organic liquid that will be coming and mixing into the aqueous layer, and that we are going to have the continuous extraction of solid molecule from aqueous layer to organic layer that is taking place. So that is called as continuous liquid-liquid extraction assembly. So here it is a process where we are not achieving any equilibrium between organic layer and aqueous layer. Now coming to problems with liquid-liquid extraction processes. Practical problem with liquid-liquid extraction can occur and include emulsion formation. So the latter can occur particularly for sample that contain surfactants or fatty materials. So what is meant by emulsion? So in liquid-liquid extraction, we are going to have, if we consider that a milky white coloration within the separating funnel is observed, that type of milky white coloration is called as emulsion with no distinct boundary between aqueous and organic phases. So this occurs when there is an surfactant. So sample that contains surfactant or fatty material, you know that if we are having organic and that is the soap action of soap or detergent, that is also based on the formation of an emulsion. So here we are not going to have the separation of solid molecule, but their boundaries will be only lost. So we are not going to have distinct phases observed. So there will be a problem with liquid-liquid extraction process when we are going to form the emulsion. Now, how can an emulsion be remedied? So the remedy is to disrupt or break up the emulsion by one step. If we have such kind of white, milky white solution observed because of the sample component, then we can do different ways of breakup of this emulsion. So we can have centrifugation of the mixture. We can centrifuge that. If it is not observed with centrifugation also, it doesn't give the disruption, then we can go for filtration through a glass wool plug or phase separation paper. So we can have this applied to separate that phases. Then we can have heating, that is placed in an oven, or cooling, that is placed in a refrigerator, the separating funnel. So we can heat the process of heating and cooling of separating funnel, which is containing that emulsion, that can be done. And then salting out by addition of sodium chloride salt to the aqueous phase. So we can add sodium chloride in the aqueous layer, that will salt out the emulsion. So addition of a small amount of different organic solvent. So some small amount of another organic solvent can lead to give us that emulsion disrupted, and we can break up and remove out the solid molecule from one phase to the another phase. So that are all about what we are having the solvent liquid-liquid extraction by continuous and discontinuous extraction technique. Now coming to the another part of volatile organic compounds, how they can be extracted, that can be done by purge and trap. If we are having volatile organics that we have to extract in the aqueous sample, we are going to use this device. So in this device, it is shown as purge gas, that is nitrogen we can use as a purge gas, and we can push that into the purge mode. In this figure, it is shown that the valves are there. We are going to have the nitrogen pushing the sample component from one phase into the another one. There we are going to have the arrow indicating how the flow of the nitrogen is taking place in that valve. And we are going to have first trapping of solid molecule into that gas. The volatile organic compound will be trapped into it. And once you trap it, the next step is the desorb mode. So we are going to have backflush of it done by the desorb gas in mode. We are going to have the sample component taken up in the backflush mode into the GC inlet system. So this is how we are going for volatile organic components or sample components that can be purged and trapped. So we can see about the purge and trap is widely applicable technique for extraction of volatile organic compounds from aqueous sample, followed by direct transfer and introduction into injection port of GC. So an aqueous sample, for example, 5 ml, is placed into glass that is called a sparging vessel. We have already seen in that figure. So sparging vessel, the sample is then purged with high purity nitrogen at flow rate of 40 to 50 ml per minute for 10 to 12 minutes. So purging indicates we are going to push or we are going to drive that solid molecule into the system that we want to have the recovery of volatile organic component that has to be done. The recovered volatile organic components are then transferred to a trap. So like a trap, we are going to place in a system or trap that can be, example, it can be of 10x at ambient temperature. So we can have the solid molecule first purged and trapped, and then we are going to have desorption of the volatile organic component from trap takes place by rapidly heating the trap. So we are having that trap heated at 180 to 250 degrees centigrade and back flushing of the volatile organic components in a stream of nitrogen gas to the gas chromatograph. So inlet system. So we are going to have that trap which will be heated to 180 to 250 degrees centigrade. So volatile component will come into gaseous state back again, and then it will be driven by again a stream of nitrogen gas to the GC system. So the desorption mode, we have seen that diagram in that. We have discussed this. So the rapid desorption from trap occurs within 2 to 4 minutes and with a nitrogen flow rate of 1 to 2 ml per minute and allows the volatile organic compounds to be desorbed in sharp plug. So the volatile organic compounds are maintained in the gaseous form by ensuring that the transfer line from the trap to the chromatograph is independently heated. So for example, we can heat it up to 225 degrees centigrade. So it ensures that all organic components are in the gaseous state. So we are going to have the heated transfer line is introduced directly into the injection port of chromatograph. And at the end of each extraction, the trap can be baked out by heating to 230 degrees centigrade for 8 minutes to remove any residual contaminants. So trap should be clean at the end. When we are having what we first extracting it, after extraction, we need to make that trap ready for the next extraction. So for that, we are going to bake that at around 230 degrees centigrade for 8 minutes, so that whatever residual contaminants are left in that trap, that will be removed and the trap will be ready for the next extraction. So that is about the purge and trap for volatile organics in aqueous sample. So that finishes with the theory and the background for classical approach of liquid-liquid extraction topic from your syllabus second chapter. So for that, we are going to have the summary mid. So the classical approach for recovering organic compound from aqueous samples, namely liquid-liquid extraction, is discussed in this chapter. So as well, we are as providing the necessary background to the approach, the important practical aspects of the technique are described. So for completeness, the alternative approach for volatile organic compounds in aqueous sample, that is purge and trap, is described. So we have discussed these all points in this lecture or session. So references, measures, RE, LCGC Europe, you can refer that. And the book that I have made this preparation from, that is Extraction Techniques in Analytical Sciences by John R. Dean. So you can refer always to this book as I have already shared to you this book. So you can go through the content and we can stop over here.